Good afternoon, everyone. Am I audible? Can someone write in the chat box? Okay, great. And kindly, for now, mute yourself whenever needed, whenever the question will arise. You will ask to unmute yourself. Okay, great. So, good afternoon, everyone. My name is Devasis Panda. I'm a Prime Minister Research Fellow at IIT Guwahati. So, for this semester, I have been allocated to this course, Structural Vibration. So this course is actually instructed by Professor Arunasis Chakraborty, IIT Guwahati, and I will be the PMRF TA for this course. So every Saturday from 3 p.m. to 5 p.m. we will meet. Now, what we will do during this 2 hour session? So basically, we will go through the concept of the current week lecture, whatever Professor Arunasis Chakraborty has covered for this week. Then we will solve the tutorials, which will be helpful for solving your assignments, and as well as we will solve different kind of MATLAB problem. As we will be dealing with the vibrational problem, we will be dealing with different kind of dynamic loading. So we will have different kind of approaches to solve them. So we will use MATLAB. So I will also provide the MATLAB script. So after every session, what you people will get that link to this recording session of the interaction, then the solved assignments or the tutorials, and whatever we have solved using MATLAB, I will provide the scripts also. So let's quickly start. Okay, so that actually the brief description what we will going to do during this 2 hour interaction session. And please mute yourself. Okay, when I will ask to unmute, or when there will any kind of question arise, you can put it in the chat box, or I will ask to unmute yourself. Okay. So the current week, first week lecture actually deals with the introduction of the structural dynamics, where we will first go through this concept like what we call dynamic system. Then we will go through the D'Alembert principle and Newton law weekly. Then we will understand the degree of freedom and simple harmonic motion, and we will solve the problem. So basically, we will follow these books. I will upload this the soft copy of these books. Whatever we will be followed during this interaction session, you will get the link of these books also. So, and you know the assessment process, like 25% of your uh, total score come from your assignments, and
Thank you, sir.
yeah.
Actually, which book will suggest? Actually, I want to planning to purchase one hard copy. Which book one book will suggest to purchase? Sir?
You can go with AK Chopra, Dynamics of Structure, or
Last one, sixth
yeah,
one.
or I will upload all the soft copies of these books, and I will give the link of this drive. So you can print any of the books also if you need, or you can need so you can get the portion of the book also. Okay, but for my opinion, if you have the AK Chopra, then it's well enough. Okay, so structural vibration, right? That means we will be dealing with the dynamic loading conditions. Dynamic loading. So first we will understand whom we call the dynamic problem, and what is the difference between that static and dynamic analysis things. Okay, so we all are habituated with and familiar with, not habituated, we all are familiar with the static loading conditions. So dynamic problem, when we call it's a dynamic problem, when actually the load and inertia acting on a structure both will vary with time, or both will be the function of time, then we call it's a dynamic problem. That means this kind of structures will experience dynamic loading. What do you mean by say dynamic loading, or time dependent loading? That means the loading will change, or the intensity of loading will change with time, like the harmonic force. Here we can say, or we can see that the amplitude of force is changing over time. But in the static case, say for example, if we have a static problem, say we have a beam, okay, and one, say for example, one load is acting over here. say for example P, or we can say one kind of block is sitting over there. So that block has some weight, so it will insert some load over here. Okay, so for the static case, what we actually know that the load is constant over time. So if we draw the load versus time diagram, we will have a straight line. Now this assumption, actually we can achieve these assumptions when the load is slowly varying. That means in the static problem, the static loading case, the load will not change or abruptly change with time. So there may be kind of like slowly varying forces which will not account for this inertia thing. So dynamic loading actually change with time. So we have only four. Okay. So first let's differentiate between them. What we call a static analysis problem, how to deal with them, and what we call a dynamic analysis problem and how to deal with them. So static analysis case, what happens with the static analysis case? Say for example, we will again consider the beam deflection problem. So we have, say for example, we have a beam. It has some mass and it has the property EI. That means it has a cross section and a modulus of elasticity. Now, for a static loading condition, if I apply a load over here and the load is static in nature, that means it will not vary with time. So what we will have, we will get like the force versus time curve, it will give a constant line curve like P and now, if the load is constant, obviously, if we look into the responses, like we are interested to find out the displacement at the midpoint. So what will happen in the static case when load is not varying with time? That means the we will have a constant deformation or constant deflection. You can say constant deflection at the midpoint. Say for example, the deflection will also constant with time, right? So as by deflection or the displacement will not change with time, that means this beam at the midpoint will not experience any kind of velocity. And if there is not time dependent velocity, will not get any kind of accelerations. So what will happen? That means the this body or this beam element will be at equilibrium, right? So there is no unbalanced force at equilibrium. How can we solve it? We can solve this problem using either equilibrium conditions. We can we already have solved different kind of problems in our undergraduate course, like in structural analysis for solving the determinate and indeterminate beam. Already we have seen that how to solve this beam using equilibrium equation. Either we can use equilibrium equation, or we have the compatibility equations, or different kind of strain displacement relations also. So by this way the static problem can be handled. That means in a static problem the load is constant over time. That means the response is also constant over time. Responses, that means first if we get the displacement and it not varies with time, then we will not have velocity, and if there is no velocity with changing with time, we will not get acceleration, so there will not change in acceleration. So we'll strictly call them the static analysis problem or the static problem. And how to deal with them? We can deal with either equilibrium equations or compatibility equations, or different kind of strain displacement relations. We can solve it. Now for a dynamic problem, what happened? Now here, instead of static loading, if I apply some dynamic loading over here, say for example here, instead of this constant loading, we have a machine at the mid span of this beam, and this machine is vibrating at a constant rpm, say for example. So that means the load now become you know dependent over time. That means that will change over time. So here we can write it like that. My load is also varying with time. That means we will have a time dependent loading. So for example, say P of t, if we want to draw and say this is the time axis. So for example, for now, say and arbitrary machine is there. We don't know it is the RPM is constant or not, it's vibrating. Okay, that means we will have that kind of force. And if it's vibrating in a constant RPM, we will have a harmonic one with some amplitude and all these things. So I will go into it later. So for now, just try to understand the force is varying with time. That means if I now want to calculate the deflection at this point, so what will happen? The displacement will also vary with time. So if I plot it over time, what will happen? Also, we will have a time varying displacement. Now, when the displacement will change, what will happen? Obviously, that mid portion of the beam will experience some velocity, and also that velocity also changes over time, right? So, say for example, Vt and T, that velocity is also changing over time. Now, when the velocity is also changing over time, that means we will have again the acceleration at the midpoint. Yes or no? Obviously. So when we will have acceleration also that varying with time, and this beam has some mass. So what will happen? There is change in inertia. Now, in dynamic problem, at the very beginning, what I have said that in dynamic problem, the load and inertia both will vary with time. Now you can understand how these things will happen. In a static analysis problem, the load is of constant. Already you have seen the load is constant over time. That means the response is also constant over time. That means there is no unbalanced force. That means there is no acceleration. So constantly we can analyze the structure using equilibrium condition or any kind of compatibility conditions. Now here we have seen that for the dynamic analysis problem, so this will be dynamic. For the static case, we have seen a few minutes back. So here we have seen that the load is also varying with time. That means at the midpoint, the deflection will also vary with time. That means we will have some velocity which also vary with time, will lead to acceleration. And when we have the acceleration, that means, and also that also vary with time, that means we will have kind of inertia force which vary with time. So in a dynamic analysis problem, the load and inertia experienced by the structure both will vary with time. On the other hand, on the static analysis case, load is constant, there is no unbalanced force, we can easily analyze them. So now here we have understood what we call a static problem, what we call a dynamic problem. Now, static problem, we know how to deal with the static problem. Now, for the dynamic problem, the motion is here, right? Motion is generated. There is time dependent displacement, velocity and acceleration, unbalanced force. Obviously, motion is there. So, obviously, the Newton's law will come into play. So, what first law of Newton says? The object will remain at rest or in uniform motion in straight line unless acted upon by the external forces. That means if a body is at rest, so it will be at rest, or if this body is moving with the constant velocity at a uniform motion, then it will continue motion. That means there will be no unbalanced force, right? So no unbalanced force, that leads to static analysis problem. So the first law, using that first law of motion, we can deal with the static analysis problem. That is, so this law is not useful for our case like what the dynamic analysis case. Now, what the second law says, a body acted by a force moves in such a manner that the time depend that the rate of change of the momentum equals to the force. A body acted upon by a force moves such a manner that the time rate of change of momentum is equals to force. Now we can interpret it is like that, to accelerate body, we need some unbalanced forces. And the force is equals to nothing but force is equals to mass time acceleration. Because to generate, if there is an unbalanced force, obviously we have already seen that acceleration will generate and the force will equals to the mass time acceleration. So let's say we have a body where three kind of forces is acting, say F1, F2 and F3. What will be the net force? Obviously, sign convention, take uniform sign convention. After taking the uniform sign convention, we can say that, okay, my net force will be equals to F1 plus F2 minus F3. Now, if my F net is equals to 0, that means it's related to the static analysis problem. That means if my body is at rest, so it will be at rest. If it is moving in a uniform speed, it will move in a uniform speed. Now, if that F net is not equals to 0, that means there is some unbalanced force. Then the acceleration will create, and the force, Newton's second law says that force is equals to nothing but the mass time the acceleration. So we will use this second law of motion to develop the equation of motion for the dynamic systems. Now, in a static case, we have seen that whom we call the static equilibrium conditions, when the summation of fx, summation of fy, summation of f z, if we are considering three dimension, fz and moments will be zero. For here also, there is a called there is a equilibrium called dynamic equilibrium, and that is mm, proposed by D'Alembert. So what he said, so D'Alembert principle, you can have this principle on Wikipedia. The actual principle, what it says, it states that the sum of difference between the force acting on a system of a massive particle and the time derivative of the momentum itself projected onto a virtual displacement consistent with the constant is equals to 0. What actually it says, if we interpreted it like that, if we have a unbalanced force, say for example, for this example, if we have a unbalanced force, say for here, Fi is my unbalanced force. Now, so here for this system, say for example, I have this is my unbalanced force. Okay, some set of forces is acting on it, and this is my unbalanced force. Now what he said, okay, if we have an unbalanced force on a body, we can consider a fictitious force which is actually equal and acting opposite to this uh, what's it unbalanced forces, and we call these situations or scenarios as the dynamic equilibrium conditions. That means what he said, okay, if a body is experiencing some unbalanced forces, and if there is an unbalanced force, obviously there will be a fictitious force which will act opposite to this unbalanced force and will be equal at magnitude of this unbalanced force, and we call this scenario as the dynamic equilibrium conditions. And the value of this fictitious force is nothing but the inertia force, that means mass time accelerations. So in a way, this two theorem says, okay, if there is an unbalanced force and if we need to solve this system, what we can do, we either we can go for the dynamic equilibrium conditions, or we can consider the Newton's second law. Then we can derive the equation of motion. So the dynamic equilibrium says the unbalanced force minus the fictitious force, that is nothing but the inertia force, is equals to 0, and this condition is called the dynamic equilibrium conditions, and then dynamic equilibrium conditions comes from the D'Alembert principles. Now we will use the two laws to formulate the equation of motions of different kind of dynamic systems. So before going to develop different kind of equation of motions, first we need to understand how to model a structure, right? Without having model of the mathematical model of the structure, it is difficult to get the response or solve the system to get the responses and all these things. So modeling, what it means, it's actually, it's nothing but a simplified description of a structure, right? So for example, we have a diving board here, right? So now I need to model it. So before analyzing this, I need to model it. So either this diving board can be modeled as a cantilever beam with certain assumptions, but depending on the situation or depending on the nature of the analysis. So I can model it as a cantilever beam with, say for example, I want to analyze this diving board for diving purpose. Say for example, here some person will so, stand over there, then jump from there. So obviously what will happen, before jumping he will jump on that position. Obviously the dynamic dynamics will generate, because uh, because let's understand, like if we have a simple cantilever beam, okay, and one point load is acting over there. Say for example, I need to construct a statue over here under with that point of a cantilever beam. So obviously the force will not vary with time. That means the displacement will not vary with time. We will have a constant deflection at the end. But for the diving board, what do we need to solve? Because some person will be here who will jump that point, then after that he will dive into that water. So what will happen? Obviously, that the deflection will change, like he will experience positive and negative deflections. So obviously there will be some velocity, there will be some acceleration, there will be change in inertia, and also this force, because he is jumping over there. So obviously the force is also vary with time. So for this problem, so this comes under the static analysis problem, and this comes under the dynamic analysis problem. But before that, we need to model this diving board as a either cantilever beam. So the simplest version to model this will be the a cantilever beam. Either we can model it using mass at a tip, or distribute considering the distributed mass. The main point over here is, first we need to have a model, and this kind of model, simplified model, is called the mechanical model. Now once we have the mechanical model, we construct the mathematical model also. Say for example, here for this cantilever beam, if I want to interested to find out the elastic curve, or the moment, or other parameters, or the responses also. So I can I can construct the mathematical model as like d2 y dx2 is equals to m by e. So we also familiar with this model. So the thing is, before analyzing any structure, first we need to have a model. What is called the model? We have two kind of model, like mechanical model and mathematical model. Mechanical model is nothing but the simplified version of this structure. Like if we have a single story building, now, how we generally model it? We model it like we consider the equivalent stiffness and mass, and then we either model it as a spring mass system, or a cantilever beam mass at the top. So this is the mechanical description of the structure, or mechanical model of the structure. Now, when we have this mechanical model, we can easily construct the mathematical model. Like when for this single degree of freedom system, when we will generate the uh, mm, equation of motion. Say for example, mx double dot plus cx dot plus kx, how it will be generated, I will tell you. So equals to 0. That we call the mathematical model, like the governing differential equation of this system. That means after solving this equation, we will get the responses and all these things. Okay. So now we have understand what we call the static problem, dynamic problem, how to model a structure. Now, in a dynamic system, there are some influencing parameters. So what parameter we need to keep our mind? Okay, these parameters may influence the dynamics of the structure. The first parameter is the mass. Obviously, every structure, or every element, or every body has some amount of matter or object. So obviously, it possesses some mass. Now, mass is very important because it is directly related to the inertia. And for the dynamic problem, we have seen that both mass and inertia, both force and inertia will change for this dynamic system. And also, I've seen that to calculate the force, we need the mass. So first, properties we need to keep in our mind is mass. Now the thing is how to model the mass. I will come into it. Now, second thing is stiffness. What is stiffness? It's nothing but the restoring force per unit deflection. So every structure must have some stiffness, high, low, medium, whatever. And stiffness actually defines the restoring force, or deals with, or caters with the restoring force. That means it controls the force displacement relations, or different kind of force distributions on the structures, and ultimately leads to different kind of responses. Now another thing is damping. What is damping? Damping is nothing but the property which makes the vibration diminishes in amplitude. That means, say for example, we have a simple pendulum. Okay, say for example, for now we have a simple pendulum, one initial theta is given to it, and leave it to vibrate. So what will happen? It will first vibrate like this. Then at a point of time, it will be back to the rest position. That means if I want to, crudely draw the motion of this, so it will have like this, like t versus my amplitude, say x. So what is happening here? My amplitude of vibration is diminishing, right? And damping is nothing but the property, or how this property will come and how this property will actually influence this amplitude diminution, or the energy diminution properties we will discuss in details. But for now, what is damping? It's like the energy dissipation mechanism. Okay, there are like here, what is the energy dissipation mechanism here? Either the wind, drag force of the wind may be there, maybe here some friction will occur is there, if it is not like proper hinge. So there can be different kind of damping sources. But the thing is, mass, stiffness, and damping, three main properties which actually influence the dynamics of a system. Okay, how we can model it, we will see one by one. So first, what we have seen, that mass is very important. So now let's quickly go through how to model a mass. So either we can model the mass as a distributed mass. Say for example, we have a beam. So beam has the cross section and the property E and E, cross section I have already said. So this beam has some mass and EI. Now in every point, if we consider that mass is distributed over the span, we call it as a distributed mass. Okay. Now if we consider that, okay, no, I want to consider the mass as a lumped mass for different kind of structure. Say for example, we have a this kind of situations where the mass of the beam is very low compared to the mass of something which is constructing on that. So we can model it like this: total mass as a spring mass system, and then here mass, this is my equivalent stiffness, and damping property we will add here. So either we can model the mass as a distributed mass, or we can consider the mass as lumped at one point, the equivalent mass lumped at one point. Because this is important, because mm, um, we will now go to the concept of the degree of freedom, where in a dynamic system, or in a dynamic structure, or any structure which is experienced that dynamic loading, we will see that to analyze it, we need to first define the degree of freedom, and the degree of freedom directly related to the displacement of the masses. So first we need to model the mass. So either the mass can be modeled as distributed mass. For the continuous system, we generally go for the distributed mass and the lumped mass condition. Now for the stiffness, what is stiffness? Is nothing but the restoring force. That means it controls the force displacement relations. So there can be linear stiffness, non-linear stiffness. So linear stiffness, generally using Hooke's law, we model it. So it's a restoring force. We considered the restoring force is nothing but it's equals to the stiffness time the displacement. Okay. So here we have seen that how to model it, and for the nonlinear system, I will I will discuss some problem how to model a nonlinear uh, stiffness. So there it will be a function of displacement and velocity both. Here for the linear case, it is only the function of the displacement. Okay, that means it purely define the restoring force per unit area. And how to model the damping? So damping, there are different kind of damping mechanism. So generally, first we will start with the viscous damping. In viscous damping, what generally considered that the damping force Fd is proportional to the velocity of the structure. So the damping force is proportional to the velocity. That means Fd is equals to some constant time x dot, and this constant we call the damping coefficient. Okay, so generally the viscous damping is modeled like this. The damping force is equals to c times the velocity of this structure, which we are interested to analyze. So c is nothing but the damping coefficient. So we will discuss different kind of damping model, like here the viscous damping thing, then we have Coulomb damping, we have different kind of equivalent viscous damping, and also rate dependent, time dependent. We will discuss on the later course of this course, later part of this course. Okay. So till now, what we have understood, okay, what we call static and dynamic analysis problem, how to model some structure. That should be mathematical model or uh, the mechanical model. Then which properties of a system actually influences the dynamics of the structure we have seen, and we have some idea about how to model mass, how to model stiffness, how to model damping. For now, we are stick to the viscous damping portion. So where the damping force is considered, is a function of the velocity. Now, degree of freedom. One of the most important concept of dynamics. Like first, what is the definition of the degree of freedom? Very important. Like definition, you should be precise with the definition. Okay. So what did say? The number of independent displacement coordinates. The number of independent displacement coordinates required to define the displaced position of all masses relative to their original position is called the number of degree of freedom of a system. So we have seen, like for this kind of structure, say for example, we have modeled a single DOF system like this. Say we have a spring which is define the stiffness which is coming from the column. We have a dashpot which is equivalent to my viscous damping device, and we have the mass, and we have modeled the mass as a lumped mass condition, and this mass can, say for example, this mass can only move to this direction x. So to understand the displaced position of this mass of this structure, how many independent coordinates we will require? Only one. So we call it single degree of freedom system. Now here, say for example, we put another spring over here. Say for example, here the mass is here, one spring is here, and another spring is here. So this mass can either move to this direction or this direction. So at a point or at a point of time, if we want to understand the position of this the displaced mass, position of this mass relative to its original position, we need 2 degree of freedom. Similarly, here we can see this mass can move independently in x1 and x2 direction. So to understand the position of the masses relative to their original positions, we need 2 degree of freedom. So degree of freedom, why it is important? Because if we want to say for example, if I want to analyze the movement of the mass like this, so I need to consider single degree of freedom system. I need to construct the equation of motion like sorry, the single degree of freedom system, and then we can proceed with the analysis. So what is the definition? The number of independent displacement coordinates. Why independent? Because to get the idea of the relative position with respect to the actual position, we need particular that amount of a degree of freedom. Like for example, we have a single pendulum, and the string is, first case, the string is rigid. So only this pendulum can move along this trajectory, like it will move up and down like this. So only we have only 1 degree of freedom, that is theta. Now if we consider, okay, my string is also deformable. It can also deform in the axial direction. So in that case, we will have 2 degree of freedom because theta and 1 is the r. Okay. Now here, if we can express this um, the degree of freedom in the term of like uh, uh, constants. So if we can construct this equation like this, f of x, y, and t, and like for this example, for this pendulum case, if obviously we can see that x square, if this is x and this is y, x square plus y square is equals to L square. So this kind of constant we call the holonomic constant, and this kind of system we call holonomic system. So we will dig into later what we say the holonomic system and all these things. So first, just get try to understand what we call the degree of freedom. Like for this system, we have two masses on two floors, and we are only interested to find out the displacement. Like, so here also we have two degree of freedom. Like here, the mass relative displacement of the mass, that means the movement of the mass in the horizontal direction, we have degree of freedom 1. So degree of freedom, why it is important? Because without knowing it or without having the proper understanding, we cannot make the mechanical model or the mathematical model of the system. That means we cannot get that uh, equation of motion for this dynamic system. So few MCQs are there, like the degree of freedom of a structure is defined as, already we have discussed, the number of displacement needed to describe the motion. The number of displacement needed to describe the motion. So the number of, here should be the number of independent displacement coordinates needed to describe the motion. Okay, so that will be that. Now, the term underdamped in context of structural dynamics referred to a system with underdamped. That means there is like insufficient damping. So we will have underdamped, overdamped systems. Later we will generate the equation of motion also. So underdamped means there is lack of damping. That means insufficient damping. Now in a structure with n degree of freedom, the number of equation of motion required to analyze it, or it's a static equation problem. So in static equation, if there are n number of equations, so obviously we need n number of equilibrium conditions to solve this equation. So obviously n or greater than n. So if n is there, so we can do with that. Like uh, the dream problem, whatever we have discussed. Like say for example, here what that question says. Like for example, there is a beam, and one load is acting over here. Now I want to analyze the beam, and it's a deterministic structure. So how many equation we will need? Obviously, first we have summation of fx equals to 0, summation of fy equals to 0, summation of mz equals to 0. Three equilibrium condition for this 2D case. But here only one unknown should be solved. That means if we go with that fx is equals to 0, we can easily calculate the reaction forces and all other things. So if there are n number of unknowns, so n number of equilibrium equations is enough. So this leads to, or this actually belongs to the static analysis problem. Now, which of the following is an example of a system with two degree of freedom? Single pendulum, mass spring system, double pendulum, simple harmonic oscillator. Obviously, double pendulum. Double pendulum has two masses, so we need to two independent displacement coordinates to define that two masses. Okay, so these are the few things related to the degrees of freedoms and all these things. So we have understood the elements of a dynamic system, whom we call the dynamic system, the degree of freedom of a dynamic system. Now how to model a single degree of freedom system. Single degree of freedom, that means the mass, or for the systems, the displacement of the mass to the relative position, we need just one coordinate to identify the displaced positions. So here we have a mass spring system where the mass can move along this x direction, either in positive x direction or in negative x directions. So how we can develop the equation of motion for this? So either we can we can use the Newton's second law, or we can use the D'Alembert principle. So using that both two, we will try to generate the equation of motion. So what is the equation of motion? It's nothing but the mathematical model of a dynamic system. What is the mathematical model? We have already discussed. Now it's the governing differential equation. After solving this equation, we will get the responses. So how we can solve it? So first, for example, using Newton's law of motion, we try to solve it. So if we draw the free body diagram of this system, what we will have? So let's try to find out the unbalanced force. So here obviously the spring is acting, that denotes the that represent the stiffness of the structure. So obviously we have seen that we actually model this stiffness as a linear stiffness. So what will be the restoring force due to that? Fs will be equals to nothing but k into x. And here, so for example, we have the viscous damper, and we have seen that how to model the viscous damper. It's nothing but the damping force is proportional to the velocity. That means we will have a constant and the velocity. So x is the displacement. Obviously, x dot will be the velocity, and x double dot will be the acceleration of the system. Okay. Now, one external force is also acting on the system, Ft. Okay. So what will be the unbalanced force over here? The unbalanced force, say for example, F unbalance will be equals to F of t minus Fs minus damping force Ft. Now what Newton's law of motion says, this unbalanced force is equals to mass time acceleration. And what is the acceleration here? If the displacement is x, so obviously mass multiplied by acceleration. So the equation of motion become mx double dot plus this restoring force due to spring action, that is nothing but k into x, plus this damping force is also there, c into x dot is equals to our external force f of t. So this is nothing but the governing differential equation of the dynamic system, or we call it the equation of motion of the system. Now solving this equation of motion, we can get the displacement x of t, can get x dot of t and x double dot of t. So there are how to solve it, how to solve this differential equation, we will see when we will solve the free vibration and force vibration problem with single degree of freedom system. For now, it is clear, okay, if we have the Newton's law of motion and if we have the clear understanding of the mathematical model and the elements of a dynamic system, we can construct the equation of motion, right? Now using D'Alembert principle again, what D'Alembert principle says, the amount of the fictitious force will be nothing but the inertia. Similar kind of thing. So first we need to find out the unbalanced forces, and then we need to equate it to the inertia forces, and that will lead to the same equation which just I have derived now, x mx double dot plus cx dot plus kx equals to f of t. Now we can develop different kind of equation of motions for different kind of structures. Like here we have solved the single degree of freedom system with the spring mass damper system, and we have modeled the mass as a lumped mass. So lumped mass, that's why it's as a single degree of freedom system. Say for example, Bob, tell me, if we have a beam, say for example cantilever beam, okay, and this cantilever beam is modeled as distributed mass, so the real cantilever beam. So tell me, what will be the degree of freedom of this system? Bob, are you there?
That'll be one.
One. Okay. So it's actually modeled as not as a lumped mass. It's distributed mass. So what will be the degree of freedom for
Okay.
this? Huh? Okay, Bob said one. The degree of freedom will be one. Okay, I will take your answer. So what will be the degree of freedom for this cantilever beam?
One.
You also said one. Okay, I'll take your answer also. Now, Arko, what will be the degree of freedom for this system?
Yeah, it's difficult to count actually.
Let's for example, there are infinite number of masses. Okay, I'm
Yeah, so that will be infinity then.
yeah. So you said infinity. Great. So which answer I will take?
Infinity.
Infinity. Bob?
Yeah, if the mass is varying, if you have different masses, then
Yeah,
you cannot even count.
there
So,
is distributed mass. Okay, and I am not defining any point for this entire cantilever beam. So I don't know how many points are there. So it crudely we can say infinite number of degree of freedom will be there. Crudely we can say not one.
so-
How?
yeah, yeah. Initially, I was considering a unit mass. So,
No, if now this cantilever beam is modeled as like this massless beam here the massless portion and here only one lumped mass is there, then only this mass can move up and down. In this condition, you can consider okay, there is only one degree of freedom, and for this case, obviously
all
there
right.
will be one degree of freedom. Okay, great. So let's derive some discuss some problems like how derive the equation of motion of this system. So I have taken this example from the AK Chopra book. So let's quickly solve it, so we'll get some idea about equation of motions, and we'll consume some time also. So
Sir,
first,
I have a small question if I may ask.
yeah, please.
Like you have said that inertia of a body is varying with time in dynamic cases, but in this case, like inertia is an inherent property which is associated with mass, right? So how can it change under a load? Inertia is the fundamental property of a mass, as we know of, but how can it vary with time? Or is it the inertia force that is actually changing?
The inertia force actually changing, not the inertia. The property actually not changing. The inertia force that m x double dot, because the acceleration will change with time. So your x double dot will change with time. So the
Yeah, so
inertia,
acceleration is changing, so inertia force, okay, understood. Yeah.
yeah. Right, the not the inertia property. The inherent property will not change, right? Inertia depends on your the cross section. Like if I have the
Yeah, the mass itself, yeah.
mass itself, yeah, we can directly say mass itself. So the inertia force will change, yeah, more
Hmm.
precisely the inertia force will change if my acceleration will change. Now if the displacement will change, the velocity will change over time. So obviously it leads to the condition
Hmm.
where the acceleration will change, so the inertia force will change, right?
Yeah, yeah.
very
Okay.
very good
Thank you.
question.
Please continue.
Yeah, okay. Now it's actually nice point, like the property inertia itself not changing, the force is actually changing, the inertia force, because the acceleration will change. Okay, so let's say, for example, we will take this problem and try to derive the equation of motion for this system. So, what we have here, two springs which are connected in a parallel manner, right? So, obviously, first we need to find out the equivalent stiffness. Now, if I draw the free body diagram of the first problem, what we'll have? Here, I have that K equivalent, the equivalent stiffness into, say here the degree of freedom is considered at U. So Ke into U will act along this direction, and the applied force is acting along this direction. Along with that we have mass. So obviously we will have the inertia force acting. Now the thing is for the parallel case, how we can get the equivalent stiffness. So for the parallel case, we know that equivalent stiffness is nothing but the sum of these two stiffnesses, like K1 plus K2. So obviously, what will be the value of this restoring force? K equivalent K1 plus K2 into U. So we get the restoring force. We don't have any kind of damping force, but we have the inertial force acting over it. So what will be the equation of motion now? So it's nothing but my inertial force m u double dot say t plus what we have, the k equivalent, the restoring force due to spring action. So k equivalent into u is equals to p of t. Great. Now comes to the second problem. Here, these two springs are, uh, you know, connected in a series manner. So for the series condition, we know the K equivalent is it nothing but is equals to that means that K equivalent, how we can solve this K equivalent for this problem. So we already know that 1 by K equivalent is equals to 1 by K1 plus 1 by K2. Now once we have the K equivalent, my equation of motion will look like that. But instead of the K equivalent in the uh, parallel case, the series case will be K equivalent is equals to 1 by K1 plus K2. If we have multiple number of springs, then we can also uh, get this by the similar way. Now for the third problem, what is there? There are two springs which is connected in series in parallel, and by with one another spring is there which is connected here. So here for this three problem, the equation governing equation of motion will be same, mu double dot t plus K equivalent into u is equals to pt. Now for the three cases, the K equivalent will change. For the first case, the K equivalent will be equals to nothing but K1 plus K2. For the second case, we can calculate K equivalent like this: 1 by Ke is equals to 1 by K1, 1 by K2. Now for third cases, first we need to get the equivalent for this parallel case. That means K1 plus K2, and we need to add with the K equivalent with the K3. So we have this and K3. So now the K equivalent will be equals to, or 1 by K equivalent will be equals to 1 by K1 plus K2 plus 1 by K3. Now solving this, you will get the K equivalent, and subsequently you can form the equation of motion of these systems. So all those things I have written over there. You can go to it, and you can also um, mm, also to derive different kind of problems. Okay. So till now, what we have covered, like we have first understood what we call a static problem or static analysis problem, and what we call a dynamic analysis problem. So for the static analysis problem, what we have seen, that the force is constant over time. That means the responses will also constant over time. That means there is no unbalanced force. So we can easily deal with this kind of problems using equilibrium conditions and all these things. Okay. Static problem, one force is there, force is constant. That means the displacement is also constant. And subsequently, we have understood what we call the dynamic problem or dynamic analysis problem. In dynamic analysis problem, we have understood, okay, my force is also varying with time. That means the displacement or the responses will also vary with time. Once we have the time varying displacement, we will have time varying velocity and time varying acceleration. That means the force and force means two kind of force, one applied force and one is the inertial force. The inertial force will also vary with time, like due to the variation of the acceleration, not the inertia inherent property, but the inertial force, what we have seen, that m time the acceleration. Great. Now we have seen uh, how to model a structure, what will be the properties of the dynamic system which actually influence the dynamic of a structure. Then we have model a single degree of freedom system. So before that, we have covered the concept of the degree of freedom, and then we have derived some equation of motion for a single degree of freedom system, and we have taken a spring problem and we have solved it. So till now, do you have any kind of queries, Bob? Or we can move with the simple
No,
harmonic.
it's fine.
Yeah, okay.
It's fine.
Yeah. So now let's talk about the simple harmonic motion. So what we call as harmonic motion first, periodic or harmonic motion. Now periodic motion actually when a motion repeats itself up in a equivalent interval. Say for example, we have some response due to this harmonic loading. So this actually, look at this, after a certain time period, it will repeat. Say for example, the time period is this t, and again it will repeat after this time period. So this called the periodic motion. That means this motion is repeated itself after period of time, or the pendulum. It's repeat itself after certain period of time, and that time is called the time period. Time period we will go into tip whom we call time period. How to, can we correlate the time period with the frequency and all these things. So like revolution of Earth at a certain time interval, the motion is you know repeated itself. Okay, and this kind of motions we call periodic motion. Now simple harmonic motion, if we go with the definition, like in a simple harmonic motion, the acceleration we have seen, uh, if the displacement will vary with time, so obviously there will be acceleration. So if the acceleration is directly proportional to displacement from the equilibrium position, we call them the simple harmonic motion. It's one kind of property, it's one of the property of the simple harmonic motion, like the acceleration is directly proportional to displacement. Like how we can prove this also. So for example, we have a structure, and this is modeled as, say for example, this is modeled as a this kind of lumped mass condition, and it can move into positive x direction up to a, and again it back to 0 and go to the extreme conditions. So what do you know from the restoring force? We know that force is equals to nothing but minus k time x, because it need to be restored. Why minus? Because that force will bring it back to the original position. That's why minus k into x. Now again, from the Newton's law, we have seen that force is nothing but mass time acceleration. So if we equate them, like mass time acceleration is equals to my kx, so obviously my acceleration becomes minus k by m into x. That means my acceleration is directly proportional to the displacement, and we call this kind of motion as simple harmonic motion. Now if we go further and inside that definition of frequency, we know the frequency omega is nothing but under root of k by m, and if we put it here, so the acceleration comes as minus omega square x. Omega is the natural frequency. What we call natural frequency? The frequency at which one structure vibrate freely. So we'll go into it later, like when we will solve the single degree of freedom system, multi degree of freedom system, damped, undamped, force, free, all these things. Then we will see that there will be like different kind of frequencies. One is like natural frequency, we will have forcing frequency, we will have damped frequency, and all these things. So natural frequency is nothing but the frequency at which structure vibrate freely. So and this can be derived by root over k by m. That means it's a property of mass and stiffness both, because both will influence. Already we have seen that both mass and stiffness will contribute to that the dynamics or the vibration of the system. So obviously that thing also get considered. So now if we go further and develop the equation of motion, so we get a is equals to omega square x. Also we know acceleration is nothing but the double derivative of the displacement, so we will have d square x by d t square. Now if we equate these two, we will get the equation of motion, and that leads to x double dot plus omega square x is equals to 0 in this form. So this will be the governing equation for this system. Now here you can write this in this form also. What we have just derived some equation of motion for there, we have write in this manner, plus say k by m in the terms of stiffness and mass. So for now let's drop that frequency thing, because we will understand deeply what the frequency is, what natural frequency, what damping frequency, what forcing frequency, and all these things. K by m into x is equals to 0. So that will be the equation of motion for this uh, single degree of freedom system and for a simple harmonic motion. Now, how we can solve it? It can be solved using the initial conditions easily. So for solving this, first we rearrange the equation and simplify it. So these things already your course instructor had covered there. So here what we have done, we have rewrite the equation of motion. Whatever we got like x double dot plus k by m x is equals to 0. So these things is written like that. D square x dt square k by m is equals to 0 multiplied by 2 into dx dt and leads to dx by dt square is equals to minus omega square x square plus some constant. Now what is dx dt? It's nothing but the velocity. Now from this equation, how we need to solve for c. Now see how can we solve c? Solve for c. C can be easily solved using the initial condition. Say for example, x equals to a. This a, that means this is the amplitude. At x equals to a, what will be this is the slope here? Bob 0, right? So we can impose this condition to find out the c, right? At x equals to a, there is no slope, that means there is no velocity. The velocity, that means dx dt is equals to 0. Now if we impose this initial condition, we will get the velocity is nothing but omega under root of a square minus x square. What is a? Is the amplitude of this motion. Now, if we further simplify it, we will get the displacement of this system as this form. X is equals to a sine omega t plus phi. What is omega? It's the natural frequency. What is phi? Is the phase angle. We will see how we can calculate that phase angle and all these things. We will go deeply. Now, once we have this, we have a relation between the time period and frequency. That is, time period is nothing but 1 by the frequency, that means twice pi by omega. That means the time period is a function of mass and displacement both. So time period is nothing but twice pi under root of m by k. We will solve different kind of problems on time period and all these things. For now, just the basics. Okay, that's how we define the problem. That's how we solve the problem or deal with the problem. So very easily we get the displacement of the system from the equation of motion. So first our equation of motion was that we impose some initial condition and we get the displacement of this harmonic motion. So where a is the amplitude, omega is the angular frequency, t the time, and phi is the phase angle. Now, if we solve one example, like here we have a simple harmonic motion and the displacement of a body is given by 3 sine 10t minus 2 cos 10t. Calculate the amplitude of the simple harmonic motion. That means you need to calculate, what do you need to calculate? You need to calculate the value of a, because we have already seen this is nothing but phi. So we have already seen that for a simple harmonic motion, x, the displacement is nothing but a sine omega t plus phi. So for this thing, we need to rearrange in this star so that we can easily get the value of a, because in that question asks to solve for a. So for example, here we have a displacement what in the form like x of t is equals to 3 sine 10t minus 2 cos 10t. So this is the displacement equation. Okay, so we have 3, we have 2, and we need to convert it in that form. So what will we do? We will first consider, say for example, 3 is equals to a cos phi and 2 is equals to a sin phi. Now rewrite the equation again. You will get in that form like x of t is equals to nothing but a cos, instead of 3 we will write a cos phi. Phi is nothing but the phase angle, mine a cos phi, and also sine 10 phi is there, sine 10t minus a sine phi cos 10t, and that actually leads to equation like that: a sine 10t minus theta. Now how we can calculate the value of a? Just using the property of the arithmetic, like a square cos square phi plus a square sine square phi is equals to nothing but we have considered 3 square plus 2 square. Now a square, take it common, cos square theta plus sine square theta is 1, so a will be equals to nothing but under root of 2a square plus 3a square. That means we will have under root of 9 plus 4 13. That means almost come as 3.605 centimeter. Please check the calculations. Okay, so what will be the amplitude? This. What will be the phase angle? Just we can get it like this. We have a sine theta or a sine phi is equals to 3 and a cos phi is equals to 2. So a cos phi is nothing but 2 by 3. We will have tan phi is equals to 2 by 3. Phi is equals to tan inverse 2 by 3. So we will get the amplitude as uh, 3.6 and the phase is tan inverse 2 by 3. And we can easily plot using MATLAB what will be the motion and all these things. So now we have understand for a simple harmonic motion how to get the amplitude, how to get the phase angle and all these things. Now let's solve a simple pendulum problem for this case also. Now, like how to generate the equation of motion for the simple pendulum. So here we have a simple pendulum where a bob is suspended of mass m, and we give some initial angle over here. Say for example, this is time t is equals to 0 over here. This is time t equals to say t1 at rest position, and it will continue its motion on this trajectory up to here. Say this is my position, t is equals to t2. Now how to derive the equation of motion for this system? So obviously when the pendulum will be here, it will experience one torque, and that will get back over here. So if we either we can go with the energy principle or directly we can get it from the free body diagram. So what will be the value of torque experienced by it is nothing but minus the weight due to gravity mg. Why minus? Because it is it help to restore the position, so minus mg into the lever arm distance x. This is the generated torque over here. So x, the position is here, and the rest position is here, so minus mgx. Again we know torque tau is equals to what is that? I, the inertia, time the angular acceleration, I time alpha. So what will be if the length of this string is L and the mass is over here is m, so obviously the inertia will be m L square. And what will be the acceleration if this is the angular displacement? So obviously the acceleration will be nothing but the double derivative of this d square theta by d t square, right? So we have torque to torque. If we equate them to, we will get the equation of motion. Now just equate them to m L square d square theta by d t square equals to minus mgx. Now rearrange the form and what we will get? Let's see. So first, what will be the value of x in terms of theta? Obviously x will be nothing but what will be that? If the length is L, so L of sine theta, right? And if we consider the assumption of small angle. So obviously x will be nothing but L theta. Now just put all these things in these equations and solve it. So now equals to m L square d square theta by d t square is equals to minus mgl theta. Now rearrange it and you will get the equation in the form of this, where d square theta by dt square plus g by l theta is equals to 0. So ultimately, which leads to the governing equation in this form, theta double dot, that means it's the acceleration plus g by l theta is equals to 0. Now where omega, the natural frequency of these things, is nothing but under root of g by l. And what will be the time period? The time period will be nothing but twice pi under root of L by G, because twice pi by omega, if omega is G by L, so L by G. This will be the time period. So this is the governing differential equation for a pendulum derived from the force balance. Like we have calculated the torque using the displaced position. We have again calculated the torque using the angular acceleration. We equate them and we form the equation of motion. Even using the energy principle, we can derive it. We will derive it after a few times, after a few minutes. So here we have seen, okay, for a dynamic system, if we understand the modeling, if we understand the components, if we understand the motion, we can derive the equation of motion either using the Newton's second law, D'Alembert principle, or there is an energy principle, conservation of energy law. We can easily construct and derive the equation of motions for this kind of systems. So this is also a similar kind of problem where what the problem says, derive the linearized governing equation of motion for the small form oscillation theta of a simple pendulum. Similar kind of thing. So here the Newton's law of motion is used. First acceleration is calculated, then the unbalanced force is equated, and similar kind of theta double dot plus g by l theta is equals to 0. We will get the uh, similar kind of equation of motion for this system also. Now, what I have just said, we can also derive the equation of motion using the energy principle. So, for a simple harmonic motion, what will be the energy, what will be the total energy, how the conservation of energy will act, we will see. So, we know the total energy is nothing but the sum of the potential energy plus the kinetic energy. Okay, so for example here, now if we see this pendulum, so this is at, say, t is equals to t1 position. Say for example this is its t is equals to 0 positions from where we are leaving this pendulum, giving it a initial angular rotation theta and leave it to vibrate, and it reach here also. So here, when we are releasing this pendulum, what is happening? We are giving the, what kind of energy we are giving, or we are inserting here? We are inserting the kinetic energy here. Then at this point, when it get here, then that energy will get converted. So I will say how this potential and kinetic energy will get converted, and ultimately the energy conservation law will satisfy. So first, if we understand how we can use this energy principle to develop or derive the equation of motion, first we need to understand the energy. So what, say for example, we have a particle x. So for this example, say for example we have a particle x and we moved it at a distance dx. So what is the work done by this particle? Work done by this particle is nothing but the force into deformation. So force, obviously the force will be the restoring force, that's why negative sign is there. So force F multiplied by the dx, because we moved the particle dx apart. So what will be the dw in the terms of force? We know that force is equals to nothing but mass time accelerations, so ma into dx. And also we know, also we have for a simple harmonic motion we have derived that A is nothing but minus omega square into x. So now if we put all these things and derive the integrate these things, we will get the total potential energy, and total potential energy comes as half m omega square into x square. And the kinetic energy is nothing but half m into v square. V, that means the double derivative of the acceleration, and v also we have derived for this case for the simple harmonic motion is nothing but omega into a square into x square. A is the amplitude of the motion. Now we have the potential energy is equals to half m omega square x square. We have the kinetic energy half m omega square a square minus x square. Now if the energy conservation law is followed, that means obviously the total energy will be constant. Now using these conditions or using the conservation of energy law, we can easily derive the equation of motions. Like for the pendulum case, we have derived the equation of motion using the Newton's law. Now if we want to derive it using the energy principle or the conservation of energy principle, how we can derive it is very easy. First, say for example we have a pendulum, the string length is L, and we provide a initial rotation theta over here at time t is equals to 0, and it reached at this point as t equals to t1, and then it's continue its motion on the other direction also. So what will be the this length? Obviously this is L cos theta. So obviously what will be this length up to the bottom? L into 1 minus cos theta. Why we need this? Because at this position when we are releasing it, we are giving that much of height change, right? So that contribute to your uh, potential energy. So if we want to calculate the total energy, so first what we need to find out, what will be the value of x. X is nothing but L into theta. If we consider the assumptions of the small angle, so x will be nothing but this. Already we have seen and derived it. What will be the velocity? Dx by dt is nothing but L d theta by dt. This is my velocity. Why we need this x? Because to calculate the kinetic and potential energy. So what will be the total energy? The total will be equals to kinetic energy plus potential energy. What will be the kinetic energy? Half m into v square. What is the v value? Velocity already we have derived this. And what is the potential energy? Mg into h. How much height we are giving to this pendulum at this position? This L into 1 minus cos theta. So mg L 1 minus cos theta. So this is the total energy equation, right? Now if we follow the conservation of energy law, so obviously the rate of change of energy over time will be 0. That means det total by dt is equals to 0. Now do the differentiations. So we will get d square theta by dt square plus g by l theta is equals to 0. In the form, just recall, we have already derived using force method or force balance method using the Newton's law. So this is nothing but theta double dot, it's the angular acceleration plus g by l, and g by l nothing but the omega square theta is equals to 0. So by this way, using the Newton's law or using the energy principle, we can derive the equation of motion of a system. Like for this case, we have derived the equation of motion using the Newton's law, using the energy principle also. Let's see another example. Like here we have a TLCD, tune liquid column damper. Tune liquid column damper. What tune liquid column damper does? Actually, it's a passive damping device. We put this kind of device top of a structure, and it helps to diminish the input earthquake energy by by sloshing action. Here some orifice is there, wave breaking, sloshing, and restoring force due to gravity we will have. So for this YouTube TLCD, where say for example we have liquid field over here, and the liquid can move only this direction, only this direction. So, how many degree of freedom are there? Only one direction the mass can move. Bob, what will be the degree of freedom? Obviously, 1 degree of freedom will be there, right? and that direction. And if this is the total length, if this is the total length of the structure or the mass, we can easily calculate the kinetic and the potential energy. So what will be the kinetic energy? Kinetic energy will be nothing but half into m into v square. M, how can we get it? Rho, if the unit weight of water or the liquid we take rho, the cross sectional area a, and the total length l, this into v square. Now what will be the potential energy? U is nothing but the mass is gets displaced by x distance. So what will be that? Mgh, that means rho into a into l into x multiplied by x distance. Now E total, calculate the E total, is nothing but the potential energy plus kinetic energy, and we have these two forms. So that will leads to half into rho a l v square plus the uh, this energy U is nothing but rho a l square. Now using the energy conservation law, what we'll get? We need to differentiate this total energy d E total by dt and make it to 0. And once we do this, we will get the equation of motion like this: dx square by dt square plus twice g by l into x is equals to 0, where the natural frequency omega naught is equals to twice g by l. For the pendulum, we have the natural frequency is under root of g by l, and the time period we also can calculate subsequently. Time period t is equals to nothing but omega by twice pi by omega. Omega is the your angular frequency. So by this way, either using the energy principle or using the law of motion or the conservation law of motion, we can calculate the, or we can derive the equation of motion. Now why equation of motion is important? Because the equation of motion actually tells us the mathematical description of the dynamic system, and after solving this mathematical description, using that mathematical description, we can calculate the responses also. So till now, if you have any questions, you can ask me. So Bob, till now, do you have any questions? So you have get some idea? Yeah, can any liquid be used? Yeah, can any liquid be used depending on the value of restoring force? So actually, if you want to know more about it, actually, recently actually, I have a patent on combined tune liquid damper. So I worked on that during my masters, and I got the patent granted during the last year December. So this is kind of interesting thing. That means that says if you use this device, generally I we have used water as the liquid because it's cheaper. It can be used for different purposes like for fire extinguishing, for the emergency purposes and all these things. And the damping device actually can reduce up to the input energy 65 to 70%. So I have this patent. So if you are interested more about tune liquid column damper, we can discuss over there.
Wow, congratulations.
Yeah, it was discovered on the last year. It's
Oh,
interesting if
great.
you want to see the reactions, if you want to see the all kind of energy distribution mechanism, all these things. So last year December,
Okay.
as an inventor, I got this patent on liquid column damper. So generally we use water. Water is cheaper. Water can be used for different purposes also, but we can also use different kind of liquid, like you know mm, magnetic kind of liquid or different kind of liquid we can check. But think water is the almost cheapest, right? And it can be used different purposes. So if you put this kind of device on the top of your building, so you will already wish like water should be there, I can use it. And any kind of other kind of fluid also can be used, like rheomagnetic type of fluid can also be used. for this kind of purposes. So it's a very interesting thing. So I have the patent on tune combined liquid damper. What we have done there, like we have combined tune liquid column damper and the liquid damper both and make a system. So that look like this. One YouTube container here there filled with YouTube container designed to design with mass ratio and all these things. So here one orifice is there, and we also use this portion as a liquid
All
damper.
right. Thank you. Thank
Two
you.
effects are there, like one is wave breaking and sloshing here, and then restoring force due to the movement of the liquid over. Okay, great. So till now we have understood a dynamic system, how we can get the equation of motion from the dynamic system, how to model a dynamic system, how to model a mass, how to model a distributed and lumped mass, the degree of freedom, all the concept I think clear, right, Rob? Bob, do you have any confusion?
No, it's fine. Yeah, maybe as we go along, we would
Yeah.
be able to know how it is applied practically so that we can appreciate it.
Oh, okay. Practically, we have applied. Practically, we have done several kind of testings for structures, different kind of structures on static table. Then only. So theoretical models actually not don't get patented. So you need to have the practical application. You need to do and show that okay, the practical application is also fine. Yeah, I will share the videos
All
also
right.
how we have tested this thing. Okay, so
All
let's
right. Thank you.
quickly solve some problem. Then we will move to our next topic. So let's solve some MCQs. Okay, for a structure subjected to oscillating force, the dynamic equilibrium is achieved when we have already discussed the dynamic equilibrium and the D'Alembert principle. When the external force equals to the inertia force. What the D'Alembert says, like if there is an unbalanced force, then obviously there will be some fictitious force acting over it, uh, which is equal in magnitude but opposite in direction. So, and that scenario we call dynamic equilibrium scenarios. Now, D'Alembert principle applied in structural dynamics to convert dynamic problem into static problem, because it actually precisely tell the dynamic equilibrium problem. That means summation of Fi, that means summation of Fi unbalanced force minus your inertia force. Say for example, inertia force I Fi is equals to 0. That means it's a static equilibrium problem. Now, next, like we have according to D'Alembert principle, the sum of algebraic product of the mass and acceleration of each particle and the force acting on it is equals to the virtual work. Now, in the application of D'Alembert principle, the term virtual displacement refers to it's an hypothetical displacement used for calculation. So if you look into the actual principle here over here, what I have discussed, like, or you can find it anywhere in the Wikipedia. Here, here states the sum of difference between the forces acting on a system of a massive particle and the time derivative of the momentum itself projected onto any virtual displacement consistent with the constraint. Why constraint? Because degree of freedom constraints of the system is 0. Okay, so ultimately our question, whatever they asked, that gets solved. Now, what is the third question? So we have solved different kind of problems till now. This kind of problem we have solved, and also we have solved problems on simple harmonic motion. Yeah, so it's a hypothetical displacement used for calculations. Now, according to D'Alembert principle, the sum of difference between the forces acting on a system and the time derivative of the momentum of the system is always equals to 0. Right? The theorem itself says. Now, from the simple harmonic motion, the simple harmonic motion is characterized by a constant amplitude, because we have seen, like in a simple harmonic motion, the motion will repeat itself after a certain period of time, and the amplitude will not say diminish. So, for example, this So here we have an amplitude. Now if it repeats itself after here, so what we will have? We will have same kind of amplitude. So it defined by an amplitude and also a phase. So here only the amplitude is also there. So amplitude. If it is a MSQ question, that amplitude and phase should be the right answer. But the phase can be zero. Here these are the tricks. Why only we are taking the display amplitude as a correct answer? Because sometimes the phase angle will be zero. Might be it is in phase, not lagging or leading. So the amplitude is the correct answer. The maximum speed of an object in a simple harmonic motion occurs when the object is an equilibrium position, obviously. Because at the end position, when the amplitude is zero, when the amplitude is maximum, there is no slope. If there is no slope, there will be no velocity, right? That means speed. So at the equilibrium position, that will be maximum. Now a body having mass m is moving with a displacement xt. Find the inertial force. Obviously mx double dot, we have solved it again and again. Okay, now MSQ type of question. Let's solve some MSQ type of question. Select the correct statements about D'Alembert principle. Okay, the net force F acting on a body and the inertia force Fi together keep the body in dynamic equilibrium. Is, what do you think, Bob? It's correct or not as per the D'Alembert principle? Obviously, the net force,
Yes, it's always. Yeah.
yeah, is always, and that actually achieve the static dynamic equilibrium conditions. Now, inertial force always act on opposite direction of the motion of the body. Inertial force always act the opposite direction of the motion of the body. What do you think? Okay, let's see. Third question. Uh, Third question. Inertial force always act to the opposite direction of the motion of the body, and inertial force is a fictitious force. Okay, these two actually is same. So these three things is the correct answer, because the inertial force is considered as a fictitious force as per the D'Alembert principle. Inertial force is always opposing the motion is also correct, and also the net force on the body is equals to the inertial force. So obviously three things are there. So it's a silly type of question. Please mute yourself. Okay, so now we have another MSQ type of question, like select the correct statement about simple harmonic motion. Bob, please mute yourself. The potential energy is maximum at the extreme point of a particle motion. The potential energy is maximum, right? Right. Because we have solved this pendulum problem and we have seen that when we release the pendulum from here at this position, so the potential energy is maximum because we have given some height and release it. Okay, now the second option says the potential energy is maximum at the equilibrium position of the, no, the kinetic energy is maximum at that position. So A and C will be the correct answer. So here the potential energy will be maximum, here the kinetic energy will be maximum, right? Now I will show you for a undamped system how this potential and kinetic energy get converted, and the equilibrium of this energy principle or the conservation of energy principle is actually established. Okay, now the third answer, let's solve quickly. Now select the correct statement about the simple harmonic motion. The acceleration of a particle is maximum at the equilibrium position. No. The acceleration of the particle is zero at the equilibrium position. Yes. The acceleration of the particle maximum at the extreme position. The acceleration of the particle is maximum at the extreme position. Right. The acceleration of the particle at the zero. No. So these two. Already we have seen that when it reaches to its equilibrium position, the acceleration will get zero. Maximum position, acceleration will get maximum. At the top amplitude, we will not get any kind of slope there. So the velocity will also zero there, but the amplitude will be maximum at that positions. So here we have another question. So where the harmonic motion, again from the harmonic motion, simple harmonic motion. So we have say x is equals to 1.25 sine 5t minus pi by 6. Now, what is that? And already you have seen that x, already you have derived that x is equals to a sine omega t minus phi. This is nothing but the response or the displacement of a simple harmonic motion. We have already derived this thing. So here, what is that a? This is the amplitude. So for example, if I want to plot it like that, so it will look like, so this is nothing but the amplitude a. This is the time period t, and again it repeats itself. So from here, amplitude, what will be the amplitude value? The a will be this. What will be the frequency? This. What will be the phase? This. So you can easily correlate which will be the correct answer. Okay, which combination of the thing will be the correct. Okay, now let's solve another problem. This problem actually I have taken from uh, A.K. Chopra book. So here again, one equation, formation of equation of motion problem. We have solved many, but still one left. So here what the problem says, develop the equation of motion for this rod. Here we have a rod, square rod, which have cross-sectional area and modulus of elasticity, length L, where mass M is suspended over there and one loading is applied, and it's a single degree of freedom system because the mass can move only downward or upward direction. So you define the degree of freedom. Now that says the ignore the mass of the rod and measure u from the static equilibrium positions. Okay, u is measured from the static equilibrium condition. Now the static equilibrium condition and massless rod, that two assumptions will tell us like we can model is the mass like this, like that will be mass where due to the spring action some fs will be there, the restoring force, the pt, that means the load is acting over there, and we have some displacement over here. So obviously we have displacement, uh, that means 1 degree of freedom system, so obviously the inertial force will act like that, mu double dot. So what will be the governing equation? Mu double dot t plus, so for now I'm writing fs. Now how we can calculate the fs? We will see fs is equals to the applied force pt. Now what is the fs for this rod? Will be nothing but ae by l. It's nothing but the stiffness k into x. So fs will be ultimately ae by l. This is my k into x. So that leads to the governing differential equation or the equation of motion as mu double dot plus the k value a by l into u is equals to u of t. Correct? Now let's solve another example. Like here we have a body of mass 25 kg resting on a platform, and the platform is moving with acceleration. Platform is moving up and down. Okay. Now the acceleration value is given as 1.5 meters per second square in downward direction. Okay, down only the downward direction. So obviously the inertial force will act upward direction. Calculate the reaction force acting on the body by the platform. So we need to calculate the reaction force, that R. So we need to first look into the free body diagram and look for the forces, and we can solve it. So here the total mass of the body and along with the gravitational acceleration, then the total weight mg is acting downward. Obviously the reaction force will be acting upward, and also we have the inertia force ma acting upward because the acceleration is acting downward. So what will be the equilibrium condition for this thing? So it's nothing but r minus mg plus ma is equals to 0. Now you can calculate R is equals to mg minus ma. M, we have the mass value 25 kg. So 25 into gravitational acceleration 9.81 mg minus, we have mass again 25 kg, acceleration 1.5, and if you solve it you will get 207.5. Please check the calculations, and if there is any correction needed, please let me know. It's a simple kind of problem. We are dealing with the simple and short problems, MCQ type of problems. We haven't entered into the actual dynamics of the structure. Then we will get that feelings of dynamic analysis. Okay, now let's solve another interesting problem. Okay, here we have a mass which is attached to a spring and a dashpot, and whole system is actually hanging to the ceiling. Hanging to the ceiling. Now, the question says derive the equation of motion of the system and discuss the effect of gravity on the natural frequency and the damping. Okay, natural frequency and damping just I have discussed a little bit, but let's solve it and we will go deep into that natural frequency, stiffness, damping. Damping, I have just talked about the viscous damping. We have different form of damping we have learned. Okay, so first, what actually happened in this system? So first, when the system is hanged to the ceiling, so what will happen? Obviously, the mass will first get displaced the amount of the static deformation, right? Mass after hanging, it will have the static deformation. Static deformation, so let's say the static deformation is del st, okay, and is depend on the stiffness property, and this will be nothing but the weight divided by the stiffness. Now what will be the total displacement of this thing? The total displacement will be the displacement due to static displacement and the displacement of mass relative to the static displacement. So total displacement x total will be equals to nothing but x plus my del st, right? So now draw the free body diagram. Here the free body diagram will look like this. The mg will act here. The catch is, like, we need to consider the total displacement in terms of relative plus static deformations. So here mg is acting on there, my spring force is acting here. The spring force fs will be nothing but k times the total displacement xt, and the damping force, obviously viscous damper is used here, so fd we model as viscous damper, and this is nothing but proportional to the velocity, that means c into x total dot, right? So now we can easily form the equation of motion. What will be the equation of motion look like? Mx double dot t, that means the total deformation plus cxt plus kx minus mg is equals to 0. Why minus mg? Because mg is also acting on it. Now if I solve this, the static deformation minus mg is a very small amount. We can neglect it to 0, and our equation of motion leads to mx double dot plus x dot plus kx equals to 0. Now from this equation we can see there is no gravity term acting or influencing this equation of motion. So obviously there is no effect on the gravity on the natural frequency and the damping part. So now let's quickly solve another problem. Like these are not the problem for the first class. Still try to understand like how this equation of motions are formed, why degree of freedom is important, why the relative and the total displacement is important, because when we are will dealing with different kind of loading, different kind of ground accelerations, so we will see we need to very often we need to deal with the total displacement. Sometimes we need to deal with the relative displacement of some degree of freedom, and sometimes we need to deal with different kind of degree of freedoms also. So here we will solve this example and we will conclude our session. Okay, say for example here again an automobile is modeled as a single degree of freedom mass spring damper system, and it says that the automobile travels at a constant speed v over a road whose roughness is known as a function of position along the road. Okay. The roughness is known. That means ug of x we know that okay, due to the roughness from the ground, some motion will generate. So how we can derive the equation of motion for this kind of systems? So for this kind of systems, first we need to find out that my what should be the relative displacement, what should be the total displacement, because the free body diagram will be very simple. Here the spring force, here's the damping force, and upward the inertia force will act. But we need to understand what should be the relative displacement and relative position. So equation of motions will be very easy, like inertia force plus spring force plus damping force will be 0. So we know that inertial force is nothing but mx double dot of t. Now this x double dot of t, what will be that? So here u is considered, so instead of x you should write u here. So what displacement? Is it the total displacement? Is it the relative displacement? So here you can see the relative displacement. Say for example, ut is the displacement of the mass. Ut is the total, u just t is the total displacement of the mass I have considered, and urb is the relative displacement with respect to the base, because we have some roughness at the base. So obviously some relative displacement will come to the base. So what will be the relative displacement if we have the total displacement ut? So obviously the relative displacement will be the ut minus that displacement due to the ground motion. So relative displacement u relative is nothing but u total minus the u due to the ground, say g of x. Now we need to form this equation with respect to the total displacement, because that mass will experience the total displacement along this direction, right? So what will be the equation of motion for this system? Mu double dot t plus c, again the relative displacement, because the c here, this c is experiencing the relative displacement, but the mass is experiencing the total displacement, and k is also experiencing the relative displacement, and relative displacement is the total displacement minus your ground displacement. So here mu t double dot, because the mass is experiencing the total displacement, the damping force is experiencing the relative displacement, also k experiencing the relative displacement. And if you simplify this equation, you will get the equation of motion in this term. So I will suggest, okay, take this example and write it down and derive it step by step. Every steps is written there, but when you will solve by yourself, you will understand why I am taking the relative displacement and the total displacement, because mass is displaced with the ground plus the total, but the spring and damping force is occurring due to the relative one, because the ground motion is there and we have a total a displacement. That total is coming from the ground and plus some dynamic acceleration problem or dynamic displacement problem. So if we subtract it from the total displacement, the ground acceleration problem, we will have the relative displacement problem. Okay, so for today, we have solved different kind of problems. We have go through different kind of concepts. I hope like the initial part is actually clear. What do you say? Or if you have any kind of questions, you can ask me. I will upload this video lecture. I will upload this PPT, the books. You will get the link today or by tomorrow, and after that you will get the link on the same day. You will get the link of this, and after second or third module you will solve different kind of problems using MATLAB, so you will get the MATLAB scripts also. So all the things what I have promised at the very beginning, you will get all these things, and which actually will help to solve your assignments. So I hope if you see watch this video carefully, then you can able to solve all the questions related to your week 1, right? So we have discussed different kind of problems, different kind of, just have patience and um, go through this video lecture. Okay, so do you have any kind of questions? You can ask me. You can unmute yourself, no problem. So Bob, why I asked this question? Because this beam problem, actually this beam, in 2 3 interviews, that question is very common. Like, tell me what should be the degrees of freedom for this beam or for a chimney. They said, okay, look at the chimney and tell me what should be the possible degree of freedom. So obviously there is a distributed mass or of the top. So obviously we will have the infinite, possibly infinite number of degrees of freedom, right?
sure.
Okay.
Yeah.
Yeah. As you try to say something, right? You want to create some WhatsApp group. Yeah, you can unmute yourself.
Yeah, good afternoon, sir.
Good afternoon. Good afternoon.
Sir, actually, I joined late. Sorry for that.
Yeah, it's okay.
If a WhatsApp group can be made, it will be possible for us whenever we are solving some, yeah, or reading, and we are having some queries, we can discuss on that.
Yeah, we can have it, but I think in that course, more than 400 people have enrolled, right? So
Oh,
if you have any kind of problem, you can directly mail to me. This is my mail ID, p.devasis@iitg.ac.in.
okay, sir.
And if possible, okay, we will create a WhatsApp group, and all these things, all the video lecture, all the assignments, all the things, and all the MATLAB code and books, whatever I have said, the NPTEL team will share with you. That means you will have a tab interaction session. There you will get the link of the video link of this video, and also the drive link to access the PPT codes and all these things. Till if possible, okay, we will do the WhatsApp group, no problem, no issue. And I can make sure that all the assignments you can easily solve it. Just go through the video. I think I have discussed uh, all kind of problems. Okay.
Okay, sir. Thank you, sir. Thank you.
So uh, do you have any other questions, Bob, or we can like
No, it's very fine. Always the beginning doesn't look very straight. So we need time to go through and
yeah,
then appreciate, yes, appreciate what has been taught. And then I think we'll be fine.
yeah.
Thank you very much.
Actually, you need to go through the video lecture again with patience. I think you will get the concept of the concept of the structural dynamics, whom we call the dynamic problem and all these things, how we to deal with that, how to form the. It's just basic. We have talked the basic today, right? Now on the next day we will talk about the free vibration problem, where we actually solve the equation of motion, how to solve and get the responses, and I will I will give you the MATLAB code how to solve these things and how to get the response. You can see the responses here live, no problem. And we see different kind of problems regarding different kind of earthquake and wind loading. So it's there. Okay, wind. Actually, I'm working on wind turbine. So wind is like with me always. And during my masters, I worked with earthquake, and that I already talked about that TCLD thing. That patent got approved. So that actually we have checked for different level of earthquake, different kind of earthquakes also. So earthquake basically, so dynamics is the core of the subject, core subject of mine. So no problem, I will help you out any kind of problems, no problem. You can directly here, or you can mail it to that mail ID. And after that, if we possible, okay, we will make a WhatsApp group, no issue. And one more thing, I
Okay,
will
sir.
upload all these books PDF version. If you want to print them, you can print it out, or you can take it as a mm, PDF with you. Great. Then we conclude our sessions here. We will meet on next Saturday. Thank you.
Thank you very much. We appreciate it.
Yeah. Thank you. Thank you.
Thank you, sir.
So we will talk later.
Okay.
Bye bye.